Hi there, welcome to your lesson on accumulated rates of change. Great lesson, let's jump right into it. Let's begin with a discussion of bacteria. And what places in a home have the most bacteria? Let's take a look. Here's a scrambled list of typical locations in a home, and I want you to, from this list, take the top three. What do you think the top three locations are in terms of the quantity of bacteria that can be found there? So which of these three have the most bacteria? Here's the list sorted from most to least. Hey, you might be surprised to see the toilet seat is on the bottom of the list. That's the least bacteria. But dish sponges and the kitchen sink actually have the most. And your toothbrush holder right there in the top three. Amazing, amazing. All right, let's keep going. So we're talking about bacteria. Here's a question we're going to look at together. A culture of bacteria is started with an initial population of 100 bacteria. So in the beginning, there are 100 bacteria, and then it grows over time. And it says the rate, I'm going to repeat that, the rate, this is the key to this lesson, the rate at which the number of bacteria changes over a 1 month period can be modeled by the function r of t equals e to the power 0.273t. All right, so the rate, this is the rate function. This is the rate of growth of the bacteria, where r is measured in bacteria per day. So find the population of bacteria 20 days after the culture was started. Okay, so here's how we're going to begin. First of all, we're told that this is the rate function. So we are given the function, and it is a rate function. How many times do I need to say rate? This is very key. Let's take a look. So for example, if we took the integral of the rate function, this would bring us back down to what? Think about this. This is the rate of change of bacteria over time. So what do you think the integral would give us? Well, the integral would give us the, I'm going to call it the b of t function, which is the number of bacteria at a certain time function. Now I want you to think back to when we worked with velocity and position, the position function. If we took the integral of velocity, it brought us back to the position function. So velocity is like a rate of change of position. Velocity is speed. It's the rate at which position is changing. So if taking the integral of velocity brings us back to position, then taking the integral of this rate of bacterial change will take us back to the bacteria function, like the position function for bacteria. Like how many bacteria are there at this time, how much bacteria is there at this time. That's what the integral of any rate function. It brings us back to the basic function, which tells us whatever that thing is at a moment in time. So integral of a rate function brings us back to the original function, in this case, the number of bacteria function. So let's apply that idea. So if we then take the integral of our rate of changing bacteria function, we will get the bacteria function. So why don't we do that? What's the integral of this? And by the way, we need a b of 20 because we're looking for the population of bacteria 20 days after the culture was started. So we're going to create the bacteria function, and then we're just going to find b20, and we'll know how many bacteria there is on day 20. All right, so let's do it. The integral. First step, the integral of e to any power is e to that same power, unchanged, except for here we have a linear exponent, so it's by chain rule, or backwards chain rule, we have to do 1 over that in front of this once we take the integral. Okay, plus c, because this is an indefinite integral. Okay, well now we're stuck here, right? What do we do? Well, first of all, let's simplify this. By the way, this can be simplified into this. We just multiplied top and bottom by 1,000 to get rid of that decimal. So now we have this. Okay, so we have our bacteria function. This function will tell us how many bacteria there is at any moment in time. And again, to get that, we went from the rate of bacteria change integral, took us back to the bacteria function. So, but we have c. Were we given some more information that helps us solve c? Let me go back in time for a second. What else were we told here? Oh, the starting or initial population was 100. Okay, so let's use that piece of information. We were told the initial population is 100 bacteria. And initial always means at time 0. So we're given a coordinate or a point on this function. We can substitute that in here. 100 for b of t and 0 for t. Like that. There's the 100, there's the 0. I'll solve that, and what do we get for c? Let's check. C equals that number there. Of course, maybe you have it simplified in a different way or a decimal, but that's okay. Let's put that back into our function, and we have our b of t function. Again, this is the function that tells us how many bacteria there is at any moment in time. And once again, just to reiterate, we began with the rate of bacteria change, took the integral, and now we're just at the bacteria function. How many bacteria is there? So now that we have that, we can finish off. Find B20, the number of bacteria, 20 seconds or minutes. No, it's 20 days, right? Wasn't it 20 days? And put it in there, and we get about approximately 957 bacteria. Great, but this looks like a lot. It gets me thinking, is there an easier way? Is there an easier way? Well, let's think about it, and let's use our understanding of integrals to figure this out. So here's the question again, and let me throw this at you. If we're talking about the growth of bacteria, because we want to know with the population of bacteria how much it grew over the first 20 days, right? It began at 100, but then it grew a certain amount until day 20. Well, to get that growth, couldn't we just do b of 20 minus b of 0? In other words, how many bacteria is there on day 20 minus how many bacteria there are on day 0? And then we'll find out how much it grew, right? And this should look familiar. So it should look familiar because whereas a moment ago we did this, we found the bacteria function by taking the integral of the bacterial growth rate function. Well, now this is something that comes from the definite integral. So instead of taking the integral, we take the definite integral of the rate function, and then we set boundaries, right, from 0 to 20. Because this integral will produce this, right? That's how integrals work. We take this, we get back to the b function, and then we subtract those two boundaries of integration, right? So I think we've just discovered a shortcut. Rather than working our way back like we did before, creating the b of t function, having to find the c value, all that work we did, we can just run the definite integral, and we'll be finding how much the bacteria grew from there to there. Well, let's try it out. Okay, so if you run that, and then you add the 100 to it, because that's how many there was initially. So it's saying, how much did the bacteria grow, because this is what this is, over 20 days, and then add it to the initial amount, and then you should have the total amount of bacteria. So how about running this on your calculator now, and we will see if we get the same answer we did a moment ago. Okay, I hope you tried it. And I hope you saw that it does produce exactly the same answer as we had here, 957. That's incredible. What a nice shortcut. And good logical shortcut too. Let's take this a little further. I want you to try another question like that. Hey, same kind of thing. It's about bacteria. We have this time an initial population of 150, and it gives you the rate of growth of bacteria here. Very similar model, a little bit different in the exponent. And let's do it both ways again. I think it's good to kind of practice both ways, to practice our integration and everything. Let's try the long way first. So we have the rate model, and we are told the population we need it in 15 days, and the initial was 150. So begin by taking the indefinite integral. Okay, again, we're given the rate of change. We know that if we take the integral of that, we will get the bacteria function. So a bacteria function is the integral of the rate function it gave us. That works out to this. Check your work now. And now solve for C. Okay, so we're putting the initial population in there, 150 at day 0. And C value is this. Now we have our full model. And we can find bacteria at day 15 by putting 15 into our full bacteria model like this. And that value should be this, 328. Hope you were successful on your path to that. But again, this is the long method, the method where we have to begin with the rate model, create the b of t model right here, with the C value, and then use the B of T model with any value we want. But now let's take the shortcut. So again, same problem, try the shortcut method. In this case, we're going to do the definite integral, all right, of the rate model from 0 to 15. That will give us how much bacteria changed from day 0 to 15. Okay, that should give us 178. Hope you checked on your calculator. And then to that, to get the total number of bacteria, the initial amount plus how much it grew, and we have our total amount. The number matches. It's incredible. So much easier, particularly if we're using our calculator for this definite integral. Okay, let's kind of summarize some key ideas here before wrapping up with one more. So here is a position function. This is what we've been talking about a lot with kinematics. So this tells us the distance that some object is from some origin at any moment in time. We can see it starts a certain distance from the origin, it goes further, gets closer, goes beyond the origin, goes behind it, and then goes past it and further again. Okay, position function. We know that when we have a position function, we can take the derivative of it and get the velocity function. Okay, and then once we have the velocity function, we can then take the integral, and if we set some boundaries here, the integral of that gives us, again, the position function with those two values plugged in. And we said basically when we took the integral of velocity, that gave us what is called the displacement. So in this case, if this integral gives us this subtraction here of positions on the graph, right? So let's say we had this was t1 and this was t2. By calculating this, we are finding the displacement, how much the position of the object changed from here to this time, and it changed this much in total. You could basically see what is this y value, what is this y value, and that's what we're doing here. One y value minus the other. It's the displacement. Okay, that was called displacement. Now let's look at another situation, because we're used to working with kinematics, but let's look at another one here. Here we have revenue, and it says revenue in thousands of euro, and over here units produced. So it's some company producing something, some number of units, and they're making revenue. Revenue goes down and then up. Okay, so on that graph, I'm going to call it RU, revenue based on units. If we took the derivative of that graph, we would have the rate of change of revenue, just like the derivative of position is velocity, which is the rate of change of position. So now we have rate of change of revenue. Then if we take the integral of that between some values, some u1 value and some u2 value, for example, here and here, then that integral will give us revenue at one location minus revenue at the other. So it is like a change in revenue. Just like here it was a change in position, here we're finding the change in revenue from one position to another. So looking at that through a different lens, velocity we know is change in distance over change in time. So the slope on this position graph is change in distance over change in time. And then when we take the integral, we are finding what's called the net change. All right, the net change, which is the displacement, the total change in position. Okay, so on this side, if we do the same thing, here, we have our revenue, the derivative of revenue, and that represents the change in revenue based on the change in units, because that's a slope. Change in revenue based on change in units, that's the slope. And then if we take the integral of that derivative, then that gives us the net change, just like we had here, the net change in revenue. And that gives us this amount here, how much the revenue has gone up or down, right? Because it's revenue at one point minus revenue at another, so it's the net change in revenue like that. Okay, so all of that, considering all that now, let's jump to this problem we have about revenue. So it says a company's revenue is based on units produced. It's the same graph we just saw. And it says we are given the rate at which revenue is earned is given by this function. So this is the rate of revenue earning. This is the revenue function, but this is the rate function. So this graph and this function are not the same, okay? This is the revenue, this is the rate. So find the net change in revenue from 2 to 13 units. Okay, so use what we just learned about integrals of rate functions in order to find this. Now let's check our work. So we run the integral of the rate function between 2 and 13. That is this, and on our calculator we get this value. So that tells us that revenue has changed by that much between 2 units produced and 13 units produced. Let's double check that. That integral represents this. all right, the revenue at 13 and the revenue at 2. And confirming on my graph, the revenue at 13 units is 29,000 and the revenue at 2 is 3.3. Subtract those and we get the same answer. Amazing.